Hello and welcome back to another VMK in the game development series. In this VMK we'll be finally implementing our light classes that we've been working on and putting them into our game engine. We'll be able to put a point light source into our scene and see how it illuminates the rest of the objects in the scene, as well as we'll play around with the directional light source and the spotlight as well. First thing we need to do is make some modification to our scene class so that we can add lights into our scene. To do this, we'll need to add some extra functions into our scene class. So let's open up scene.h and take a look at what we have here. At the top, we are including all the different .h files that we'll be using, and since we're going to be using our lights now, we need to include our three new light classes. Now, notice we don't include node_light.h since each of these actually include node_light.h in their own .h files. There are a bunch of private functions we need to add to get our lights to work properly. We need to create this function called addLight, which will allow us to add a light into our scene. We'll need a function to delete all lights. This will be used in the destructor whenever we're done, so it's going to delete all the lights that we originally created. We have a getLight function call, which allows us to get a specific light pointer back to us. So if we want to manipulate a specific light, we can do that. And then there's lights enabled and lights disabled. These are called within a render function. And you'll see in a minute how we use all of these. The other thing we need to add is under, I'll put it right here underneath error handler, we have two member variables. std vector is a dynamic array which we have access to through the standard C++ interface. What we can do with this is put pointers into this vector so that we can keep track of all the lights in our scene. And that's what's going to happen whenever we call this addLight function up here. So this member variable is going to contain all of our lights. Then we need a counter here which is going to count how many lights are currently turned on. And we'll use this so that we don't go over our maximum, which is defined in our nodeLight class. Okay, let's go and add a light into our scene now. To do that, we'll go into our scene, initialize, and at the bottom here, after we've initialized our third house, let's go create a light source. Now, the light source we're going to start with is just a point light. So we create a pointer to nodeLight point, and then we allocate new memory using nodeLight point constructor here. Then we set the position of this light source, and I'm just going to move it up a little bit in the Y direction, so it's going to just stand a little bit above 0 here, 2 units above. And then I'm setting the ambient, the diffuse, and the specular color to some values here. And then after we set all the parameters, we then call the addLight function to save that pointer into our member variable. So let's now go and write the addLight function for our scene. So I'll just put it right at the very bottom here. After the update, we have addLight. So it takes a pointer to a node light, and what we do with that pointer is we just push it back onto our member variable here, mlights. And again, mlights is that standard vector which is a dynamic array. And this function returns the current size of this array minus 1. So in other words, it's going to return a unique ID for this light that we've just pushed onto our stack. So initially, when we put a light source into this member variable, it should return 0, since the size of this member variable will be 1, and then we subtract 1 from it, so it's going to return 0. As soon as we push the second one on, then it's going to return 1, and so on. We need to know these ID numbers so that when we want to modify a light, we can then use this ID number if we wanted to. The other thing we need to do is, since we're adding new lights here in the constructor, we're calling the new operator, which means we need to be able to call delete somewhere so that we can deallocate the memory we're creating. And that's going to happen inside the following function. So we have delete all lights, and this goes through our member variable here for all our lights from 0 up to the current size, and it deletes every single pointer that's stored in that memory. After it deletes them all, then go and clear our member variable so that the array no longer holds any data inside it. Now that we have this function, we can go and add it into our clear up. So anytime we're done, or anytime we want to clear everything in the scene, we just go and delete all the lights. The other functions that we just added to scene is getLight, and what we do here is we pass in an ID number, and again, the ID number is the same ID number that addLight returns to us, and depending on the ID number that gets passed in here, we do a little error check to make sure it's a valid ID number. If it is, we return that pointer for that node light that we requested. If this ID number is invalid, then we just return 0 or null. Now when we want to go and render our scene, we need to go and update the following function. Where is update? Here it is. So before we render any objects, we first turn on the lights, which is done by calling lights enabled, and then after we render our objects, we go and call disable lights. Oh, my mistake, it's actually called lights disabled. Okay, so let's write these two new functions as well at the very bottom. Lights enabled works as follows. We first check to see what is the current size of our member variable for our lights. If it's equal to 0, then that means we haven't created any lights in the scene, so lights enabled doesn't have to do anything, so we just return automatically. If there are lights in the scene, we then set the light counter to be 0, and we create a local variable here calledplight, which is a pointer to a node light. We then iterate through every single light source we have in memory in our member variable, and we check to make sure that our current light counter, which is this value here, we check to see if this is greater than or equal to the maximum number of lights that we're allowed to have. If this is true, then that means we cannot add any more lights to the scene, so we just break out of this for loop. If this is false, which it should be initially, then we get our light pointer from our member variable here. We check to see if this specific light is turned on. If it is, we then go and render it using the specific lights render function. If this is turned off, then we don't go and render it, and we just go through the loop. Now notice what happens when we do render it. We pass in our light counter number, but then we post increment this value. So initially we set the light counter to be 0. It's going to go through here, and when it comes in here, we're going to call render with a value of 0. But after we call render, we then increment this counter, so it automatically increments to 1. So the next time we go through, render is going to be called with the value of 1 here. This is just a quick way of incrementing the counter. I could have done this in 2 steps, passing in Emma underscore I light counter here, and then on the next line increment the counter, but it's just easier to put it all into one line. The other function that we're going to add here is lights disabled. Now what this one does is it goes through all of our lights again in a for loop. So it checks to see if there are any lights in our scene. If there are, then the size of this member variable will be greater than 0, so continue through. Again, we reset our counter to 0. We have a local variable here that points to a node light. We go through every single light source in our member variable. We check to see if the number of lights here hasn't exceeded the maximum number of lights. If this is true, if it has exceeded the number of lights, we just break out. If it hasn't, then we get the current light source. We check to see if it's been turned on. If it has, then we go and disable it. So in other words, whatever gets turned on here automatically gets turned off here. We need to do this so that when we have a font engine implemented into our game engine, we can then render items on the screen properly. If we don't turn off the lights here, then it'll make it more difficult later on. So I just added this functionality right now, even though we don't really need it. We will in the future though. Okay, let's save this, and let's see if we can compile this. We did get some errors here. Alright, STD is giving us an error here because we need to go into our precompiled headers and add an extra include. So let's go into our game engine, our header files under main, and I'll put it here underneath stdio.h. We need to include vector, which is the SDL vector, or also known as an array. And try compiling this again. Okay, that looks like that's the only thing we needed to change. Now if we were to just go and run this, our light sources wouldn't really work. Actually, let me go and show you. Let's build the application. And give it a run. Okay, you'll notice that the scene itself is pretty dark. So our light source, which is hovering up here, doesn't seem to be doing anything. And there's a couple reasons for that. First of all, I want to modify the ground since it's a little bit small from the last time we changed it. Where was this? I think it's at the very top here. Yeah. We want to increase the size of this. Maybe make it 20 long. I think that should make it look so that the houses are not floating. Okay. And maybe make it a little wider as well. Maybe I'll make this 10. Okay. The ground itself is currently of size 1 by 1. So the resolution of this ground isn't very good, which means that the light source, which is above, happens to be right in the middle of this of these two triangles, so we can't really see the light in effect. If we were to go and increase the number of divisions here, let's make this 20 by 20, we should be able to see our point light source. Okay, so now you see a nice sort of gradient in the middle over top of where the light source should be. You can't see the light source because we're not rendering anything in place of where the light is. We can only see the effect of the light on the ground here. Now notice something interesting. The light is affecting the ground, but the light is not affecting our houses. Our houses are sort of dim and dark, but the lights are not affecting it. Well, the reason for this is the light source itself has normals defined for it, but our houses don't. So if we go into our class for our objects and our ground, under render, you'll notice here I added GL normal 3F, and it's pointing straight up. So that means that we have a normal for this ground, and it happens to be pointing straight up. Normals are used for calculating lights, and that's why on the ground we can see the light. But if we go into our house, you'll notice we don't have any GL normal functions here. So we didn't define the normals. So for lights to work on our house, we have to go and define those normals. So let's do that right now. Let's make some more room here. So to start, we need to go and add a member variable into our house.h. And I'll put it here underneath the vertices. And we need 6 of them. Since the house itself has 6 distinct faces, there's the front, the sides, the 2 sides, left and right, and the back, so that's 4. And then the roof itself has 2 faces, and each of those have a different normal. Now the way that the normal is defined is it's a vector that's perpendicular to the face, so it's the vector that's pointing out of the face that we're talking about. So let's go into our constructor and go define these 6 normals. We'll just do that here on the bottom. We initialized the 6 vectors for the normals for the 6 different faces. We'll start with the easy ones, which is the front, the right, the back, and the left side of the house. The normal coming out of the front face is in the Z direction, so we have 0, 0, 1. The normal coming off the back is the opposite of the front, so we have a negative sign for the Z. The right and left are coming straight into the x-axis, so 1 for the x-axis and then -1 for the other side of the house. The two normals for the roof, we need to go and calculate the normal value. What I've done here is used a two-dimensional perpendicular to calculate the normal for the roof. If you want more details on how to calculate a two-dimensional perpendicular, I recommend you take a look at the Math VMK. So first thing we do is we get the magnitude of the direction vector of the roof, and then we get the direction vector x component and the y component. And then using those two values, we can then generate the normal for the right side of the roof and for the left side of the roof here, just by using the y direction, the x direction, and 0, and then the -y, the x, and 0. After having the normals defined, we then need to go and use them inside the render function. So here I've went ahead and added in the normals. For the roof, you see, before we go and render the polygon, we now have to call GL normal 3F and then specify which normal we want to use. So for the roof front, we're going to be using the same normal as the front of the house, so that's normal 0. And again, I've labeled them here, front, right, back, left. So the front is normal 0. Then we have the roof back, so we're going to use the back of the house, which is normal 2. The right roof and the left roof, we have normal 4 and normal 5. And then we have the house itself. So we have the front of the house, again, we reuse normal 0. The right side of the house, normal 1. The back of the house, normal 2. And the left side of the house, normal 3. Okay, let's try to compile this now to see if we can go and render this. Looks like we have some errors in house.h. It looks like we didn't include vector3.h at the top here. Yeah, we didn't. So that's why we're getting those errors. So we can just go include vector3.h and try that again. Oh, and I can't find vector3.h because in the project we probably forgot to include the right path. So we're working in house, which is in the object library. So let's take a look at the path properties. Vector3.h isn't part of the object library, it's part of the math library, so we need to make sure we include the math library path here. And try that again. Okay. I did notice one warning here. Conversion from double to float. Oh, right. Whenever we're using numbers like this, we should put an F at the end so that we specify that this is going to be a floating point number. Otherwise, it's going to take it as a double. So if we put an F here, that should correct that. Okay, now let's build the application and see if we can run it. Okay, now you can see that the houses are actually rendered correctly with the light source up in the sky. So you notice the front faces are brighter, and then as we go around to the back, we notice that they're darker. And that's just basically the calculations that OpenGL does for us due to the normals that we specified on the house. Okay, so that works really good. Now the other object we had was the triangle. So we might as well go and modify the triangle now and add a normal to this as well. So first thing we're going to do is in the member variables here, create a variable to hold our normal. Now our triangle is just made up of 3 points, and the normal itself has to point directly out of the face of the triangle. If you go into one of my math VMKs, you'll notice that I posted a method for calculating a normal to a surface giving 3 points. So that's the method we're going to be using for the triangle. Let's go into the constructor and put that algorithm in here. So the first thing we need to do is calculate two vectors that are on the face of this triangle. So we have vector 1 and vector 2. And then we get our third vector, which is our normal vector, by crossing vector 2 with vector 1. We then normalize that vector, and the result of that is our normal that we specify into our member variable here. Let's go and compile this and see what happens. Again, we don't have vector 3 declared in our triangle.h, so we can go and add that in here. And let's go and try to compile that again. And the next thing we need to do is, inside our vector class, we don't have a minus operator defined, nor do we have a cross or a normalize defined. So we need to go and write these functions. Let's go ahead and do that. We can open up the math library and go into the vector 3. And I'll add them right at the very bottom here. Okay. The cross product is calculated using the formula in the math VMK. So there it is there. And normalizing is also in the math VMK. So we just take the magnitude of our vector and divide each of the components by that magnitude. So if the magnitude itself is small, close to 0, we then change the values all to 0 since we can't divide by 0. Otherwise we go and normalize properly. So we take the current value for x and divide it by the magnitude, current value of y, and current value of z individually. Now the other thing I noticed here was this minus operator has to work on vertexes rather than vectors, because v1 and v2 are vertexes that are passed in here. So we have to go and modify the vertex class to be able to handle this negative operator. Let's open that up now. Vertex. In here we need to overload an operator, and then we can go implement it in vertex3.cpp. And I'll just do that on the bottom. Okay. So what this does is it takes the current value of the vertex and subtracts from it the value that we're subtracting. And again, we do this component-wise, so we take the x's, subtract them, the y's, and the z's, and the return value is a new vertex, so we create a new vertex using our constructor here, and we just return it. Now, because of the way we're handling this, this means that this here is going to evaluate to a new vertex value, which gets returned from that operator overloading. But this here is a vector 3. So we need to create a new constructor that constructs a vector out of a vertex. And to do that, we'll go back into vector3.h and create that constructor. And I'll put it here right before the destructor. So all we're doing is we're taking in a vertex 3 and assigning all the x, y, z components to the x, y, z components of the vector. We don't need to do any other checks or anything like that. Okay. Those changes I think should get rid of those error message we saw here. Let's try to build and see. Looks like we've got quite a few errors. Okay. Okay. Vector 3 here doesn't know what a vertex is, since we probably didn't include vertex up here. So we can go include that and try rebuilding again. It's a little better, but I think I still saw some errors up there. Okay, cannot open vertex 3.h. Okay. Again, this is the problem with the paths not being set up properly. So vector 3.h is inside the math, and vertex is inside object lib. So we need to go and adjust the paths here. So here we need to add object lib. And that should correct that problem. Okay, that worked. Well, let's go and build this and run it. Okay, we should see no change because we don't have any triangles in the scene yet. But let's now go and render a triangle to see if that normal is working correctly. So we'll go back into our scene, and do we have a triangle? We do have a triangle here, but we're just probably disabled it in the render triangle window. Okay. Let's see if we can see our triangle. Okay. So the triangle itself is translucent, which makes it difficult to see the effect of the light on it. Let's change the color of it to make it a little more visible. And we can do that just by changing this last value here to a 0. Or actually, we can remove it altogether. So this should give us a yellow triangle in front of our faces. Okay. And you can see now the light, which is located up above, is shining down on the triangle, lighting it up. Now you'll notice that the lighting kind of looks funny because it's only affecting the one corner, the top right hand corner, and not the other ones. And again, this is caused by the resolution of this triangle. We don't have any extra vertices defining this triangle, so the lighting calculation isn't ideal. But we can play around with the triangle. Let's move some points around. Let's see what we have here. -1, 1, -1, and 0. Okay, this must be the bottom point. Let's move the bottom point towards us a little. If we do this, it should point upward. Yeah, it does. So we can see the light on it. And if we move the bottom point backward, we should see it gets darker. Let's make it at 2. Something wrong with our calculation because it doesn't look like that normal is working properly. Let me double check one thing. In the render, that's our problem. We never used the normal that we calculated up above. So just up here, let's go and call GL normal 3FV and pass in the normal value. Now we should see the correct lighting on the triangle. There we go. So the triangle itself is pointing downward, so the normal is pointing away from the light source, so the surface looks dark. If we move that point, the bottom point on the triangle, so it points upward again, make this a 0, then we should see that the triangle gets brighter. And it does. Okay, so the lighting now works for the triangle properly. Okay. Well, let's disable the triangle rendering again and play around with the other light sources that we've created. So far we've only played with the point light source. Let's go and add, instead of a point light source, let's use a directional light source. So all we need to do is change our pointer from a point to a directional, which means our constructor has to change. And then instead of setting the position, since directional light has no position, we need to go and set the direction. And let's see. Let's make a sort of point downward and towards the houses. So that would be minus 0.5. Downward would be minus 0.5, and in towards the houses, let's make it 1. Or I guess it has to be minus 1 to be towards the houses. Okay, and we're going to leave the color the same, and I think that's all we need to change. Let's build this and run it. Oh, it doesn't take 3 arguments. Oh, it takes a vector. Okay, let's change this. Vector 3. And run that. Okay, the scene is pretty dark. Oh, and the light seems to be pointing from behind. I think I got my coordinate system mixed up here. Let's take a look. If we change this to a +1, what do we get? That lights up the front, and looks like the light source is up above here. That's interesting. Let's play with it in this fashion. Make the 0 and make the light source point straight down. So we'll do -1. And it doesn't look like it's pointing straight down. It looks like it's probably pointing straight up. It looks like the coordinate system here is reversed for some reason. Let's try this. Yeah, this one points straight down. So for some reason, the coordinate system for this direction is reversed. Well, let's take a look at MSDN and how they define the direction here. In GL Light, if you scroll down to the GL position parameter, we see here it says the default position is 0010. Thus, the default light source is directional, parallel to, and in the direction of the -z-axis. So even though they're in the plus direction, it's in the minus. So there's a negative logic here that they've used. To make a little more sense to us, I think it would make more sense to do this. So if we want the directional light source to point straight down, we would say -1, and then in our light class we can go and update it to actually use the negative value that we pass in. This would be under directional light source. Set direction. So whatever value is passing in here, we're going to go and take the negative of it and store it in our member variable. If we make this change, we have to be aware here that getting the direction now is not going to be correct, because we return our member variables, but the member variable is actually the negative direction. So we need to go and create a new member variable that's going to contain a temporary variable, which we can go and set the negative direction of our position and then return it. So to do that, we'll go into the .h file, and under private members, we'll create float. Just create 4 of them. And in here, we need to go and assign some values to them. And the values we're going to assign is the negative of whatever's stored in that member variable. Like this. And then we can just, instead of returning our position, we're going to return our temporary variable. And that should correct the direction. Okay. Let's go and build this. And just want to double check our Where's our scene? Scene.cpp. Okay, so now I'm making the direction point straight down the Y, so we should see a bright light. Okay, and we do. And then again, if we're to change this back to what I originally had, -1 or -0.5, -0.5, and in towards the screen, which would be -1, then the light source should be up to the right, if I've done this correctly. Okay, and that's what it looks like. It's somewhere above here, since that face is brighter, and it should be dark behind here. Yeah. Okay, so that's our directional light. Go through here and play around with the parameters for the point light source or directional light source. Get familiar with how they work. Now let's play with the spotlight, which is the last lighting type we've created. So here we've changed the pointer to be a node light spot, and we changed the constructor to be node light spot. And I'm positioning the spotlight to be 2 units above the surface of the ground. And initially we're going to point it straight down, so we have -1 for the Y value. Let's build this and run it. And you'll notice the spotlight itself doesn't really look much different than a point light source. And the reason for that is we never set the cutoff or the exponent value for the spotlight. What we can do is, under the default constructor for the spotlight, where is it? Node light spot. Here we can specify some default values. So m_f cutoff will set to be 45 degrees, and the other one, which was exponent, we'll set this one to be 50. This is just the value. Now, if we use the default values, we should be able to see a more focused beam of light. And we do. We see it's pointing straight down here, directly on top of us. We can change the direction of it by moving this vector here. So currently it's pointing straight down. Let's make a point sort of towards the houses. So -1 down and then -1 towards the house. See what that looks like. Okay, so we moved it now sort of down there. And if you want, you can also play around with those exponent values and things by using the function itself. Set exponent, for instance. You can change the exponent to whatever you want. Let's say 20. Oh. And we can also change the cutoff. Set cutoff. Can make it smaller or bigger. I think right now we set it to 45, so maybe it'll make it a little bigger, 60 degrees. So there we go. The light source has a bigger beam now, and looks a little dimmer. So there you go. That's how you play around with the light sources. Go around, get a feel for how they work, and now that you have light sources in the scene, you can add things like, for instance, a sun. You can do day and night. So if you're playing during the game, if you're playing the game during the day, you would have a light source, a directional light source, shooting down onto the terrain, so everything's nice and bright. But then as it starts to get nighttime in the game, you can move the position of the light source down, and then everything will start getting darker and darker to simulate day and night. So that's very easy to do. Other things you can do with light sources is, for instance, if you're doing a game in a dungeon, well, you can specify a torch that the user's holding to be a light source. And then as they're moving through the world, different parts of the world will be lit up. And then if they move out of a room, then the room will get dark again. So that's kind of neat as well. So play around with the light sources. You've got 3 to play with: directional, spotlight, and positional light source. You can mix and match them. You can have multiple light sources in a scene. The number again is specified by your video card, but you should be able to use 8 with no problems. If you want to use more than 8 light sources, then you're going to have to be turning some off and other ones on in the appropriate order. Okay, so that's the lighting tutorial. Come back again next time where we'll be adding more functionality into the scene.